which is, supposing, let's just for a moment try and understand in different graphical forms. Okay, so I'm going to now restrict itself to sigma 1 and sigma 2. Let's say sigma 3 is equal to 0. Okay. Let's now plot Tresca condition. Okay. Now, Tresca condition says that
max
sigma 1 minus sigma 2,
max
sigma 2 minus sigma 3, sigma 3 minus sigma 1 goes to a limit. Okay. The first thing that I do here is, supposing it is uniaxial tension, then it says that if it is sigma 1 and sigma 2 equal to sigma 3 equal to 0, then sigma 1 is equal to K. Okay?
Yes, sir.
And this will be the yield value.
Yes.
This K can be found out by doing this experiment. So in this, if I did that, let us say I got the value here, which is sigma y. Okay. Mind you, the material is isotropic. So if I conduct the test with sigma 2, at what value of sigma 2 will it yield? It will yield at the same sigma y here. Correct?
Yes,
Yes, sir.
Yes, sir.
Now, let's take one more scenario so that we can get some idea. Let's say this is nothing but sigma 1 is equal to sigma 2.
Okay, biaxial.
If I look at this maximum of these three, sigma 1 and minus sigma 2 goes to 0.
Okay.
Yes, sir.
Right? And therefore it has to be
Sigma 2 or sigma 1.
Sigma 2 or sigma.
sigma 2
Sigma 1.
equal to sigma
That's
1 is equal to K.
Okay.
Correct?
Yes, sir.
So what
Yes.
I get is
Yes.
this as the locus of the yield function. Since it is symmetric, I can easily do the same thing over here and I'll get it to be something like this. In this zone, sigma 1 is negative, sigma 2 is positive, and sigma 3 is equal to 0 in this zone. Correct?
Yes, sir.
Naturally, if you look at it carefully, sigma 2 minus sigma 1 will be the maximum value.
Yes.
Yes, sir.
Or in other words, if sigma 1 minus sigma 2 goes to sigma y, that's the condition that we will have in this zone. Yes? So if you do
Yes,
that,
sir.
it is nothing but the line that connects these two.
Which means sigma 2 or sigma 1 is equal to sigma y. That is why it is aligned, right, sir?
Correct. So sigma 1 minus sigma 2 is equal to sigma y. This is nothing but sigma 1 is equal to sigma y. This is nothing but sigma 2 equal to sigma y. So this, as long as I am within this region, no yielding occurs. Correct?
Yes, sir.
Pictorially, I have represented. But what I notice is there are corners over here. Why am I so bothered about corner? We also said something. Oops, sorry. We also said something, which is, if I take plastic potential to be the same as yield function, then the flow occurs in the direction of, we discussed this earlier,
Stress applied at
in the direction that is normal to the potential lines, or in other words, flow lines are perpendicular to potential lines. You remember this?
Yes, sir.
This comes from the concept of flow net.
Flow net.
Right? In flow net, I draw potential lines. I draw flow lines. Flow lines are always perpendicular to potential lines. If I take the yield to be the plastic potential, then the flow line is perpendicular to potential line, or in other words, dou F by dou sigma, which is nothing but the normal to the potential F, is the direction of, I'm just going to put some constant. I'm going to put it as some phi bar times dou F by dou sigma is equal to epsilon dot P. The flow is represented by this, is always normal to dou F by, normal to the potential F. Why am I bringing this over here? I'm bringing this over here just to ask, well, can I find out the flow of this particular kind of surface? Okay. Let me pass over here, take questions from you.
You're calling F sigma as a plastic potential.
Correct. So that's an assumption I make. Because as F gets to a value which is nearer to K, this flow starts shorter. Alright? So depending on the level of this potential, I will tell you whether the flow is going to occur or not.
Okay.
It is sensible to use plastic yield function as a plastic potential.
Okay, it's a single number. This function gives a single number.
It's a single number. So in a flow line, it is like, in the flow net, it is like a potential value or head value.
That will tell you whether flow is going to.
So here, what are we comparing the potential to?
We are comparing the potential to how the flow is occurring.
I mean, in fluid mechanics, it depends on the head difference, right?
That head difference here is nothing but the potential. F of sigma. See, F of sigma value is the one that matters to me. If you look at it, this is F of sigma. Is it not?
Yes, sir. Yes, sir.
So if this is the potential line, the direction of the flow will be like this. Yes or no?
Yes, sir.
The direction here will be like this. Correct? The direction will be like this here and so on. One problem that occurs is at this point, it could be either this or this or this or this. It is not unique.
Yes, sir.
In flow, it is called the corner point.
Corner points.
I wish to avoid these corner points because in modeling, it becomes tough for me to estimate what would be that flow direction. People assume, okay, let me take this direction, a linear combination of these two directions. But all those are just making assumptions. Ideally, if it is rounded like this, it is easy. Supposing this is rounded like this, 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 I don't have this problem. And what is this surface? This entire surface? There is nothing but n. It is related to n infinity. Supposing instead of n infinity, if I take something which is nm, where m is not equal to infinity, perhaps I will get rid of these.
Smoother.
Now let's go to von Mises. What does von Mises say? Sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square is equal to some k. Okay, we did this exercise. We said, okay, if it is uniaxial, I should find out what is this k. And we got it to be
Root 3 by 2.
root 3 by 2.
2 or 3 by 2, yeah.
This is k square. Okay. Okay. So supposing, how did I do this? I did a uniaxial tension test, correct? If I do uniaxial tension test, sigma 1 will go to sigma y at yield. This is clear, right? Yeah?
Yes.
Yes, sir.
Now, if I do that, at this point, this is already sigma y. This is already sigma y. Right? Can you substitute for finding out on what point of this sigma 1 equal to sigma 2 will von Mises lie? Can you quickly do that exercise?
Corner point itself. No?
I can't hear you.
So that corner point itself.
The corner point itself, is it not? So in
Yes,
a
sir.
way, it is like this. You agree with me? Remember, it's a square quadratic function, so it is something like this. Yeah? Similarly here, it is something like this. And if you do it here, it will come out to be something like this. And this is an ellipse, which is the von Mises yield surface.
The ellipse you draw over the
Yeah.
corner, it is outscribe. Can it be means inscribe also?
No, in this case, I have done a uniaxial tension test.
Okay.
It is a uniaxial tension test, and I'm trying to match using the uniaxial tension test, and therefore I got this. Supposing I did something else, which is, say, if I did the shear test, pure shear test, pure shear here lies over here along this line, where sigma 1 is equal to minus sigma 2.
Okay.
Understood?
Yes, sir.
Right? Now, if I did that, I would probably get something like this as von Mises.
Yes, sir.
It depends on what test I conduct. No, it all depends on the experiment that you conduct. This is a uniaxial test that I conducted and showed it here. Another way of looking at it is, let's take a three-dimensional scenario. So this is sigma 1, sigma 2, sigma 3. Now, this is sigma 1, sigma 2, sigma 3 space, correct? What is this? This is sigma 1, sigma 2, with sigma 3 being
0.
0. So in this case, if sigma 3 is equal to 0, and it is not dependent on hydrostatic stress, along which line there is no change that I will notice. It will be along the hydrostatic line.
Hydrostatic. Yes.
Or in other words, if I draw a line, supposing I have something like this, which is sigma 1 equal to sigma 2 equal to sigma 3. I call this as hydrostatic line. And if I view from here, how will this look like? How will this look like? That's the question.
Point, sir. Point.
It will look like a hexagon.
Straight line.
It
Straight
will
line,
look
sir.
like a,
Sir, it's a plane, sir.
Perfect
It's a
hexagon.
plane.
precisely, it will look like a hexagon, right? There
Yes,
is,
sir.
let me see if I can explain to you through this. So if I see it like this, it is like this. If it is like this, if I had cut it off in a plane that is, let us say, if I cut it off in a plane like this, if I cut it off in a plane like this, what will happen is this length will increase,
Yeah,
this
elongated.
length will decrease, right? In a way, if I'm showing this, I'm sorry,
Yes,
this
sir.
is expanding and this is expanding. These two are expanding. Why? Because I'm cutting along this line, along this line.
Yeah.
Yes, sir.
You understood?
Okay. Hmm.
Supposing I see from this side, they will all look in such a way that they are 180, 120 degrees apart. What am I doing here? I'm seeing from this hydrostatic line, like this. Okay?
Yes, sir.
When I do that, what I will get is something like this.
Yes, sir.
Don't mind my drawing, but this is a regular hexagon that I'll get. And how will one missus look like? One missus will look like a spherical,
Circle.
sorry, circular cylinder. So while this is a prism, is a
Cylinder.
prismatic this thing that extends
Hexagonal
along the.
cylinder.
Are you able to see?
Yes, sir.
This is the hydrostatic line. This prismatic
Cylinder. Hexagonal
boundary
cylinder.
will extend through infinity. It will be a long prism that I will see. On the other hand, if it is one missus, it will be a circular cross section extending completely, or in other words, it's a cylinder. Okay?
So that will happen when we see from the
From the hydrostatic line. Hydrostatic line is equally apart from sigma 1, sigma 2 and sigma 3. Or in other words, sigma 1 equal to sigma 2 equal to sigma 3. Okay? We call this as pi plane. I'm not going to go into details, but I just wanted to show you what is it that you really get. Okay? You will see that this regular hexagon is inscribed in the circle. Okay. It also tells me if I know this region, I can just replicate in all the other regions. Is it not? If you notice, this is the maximum difference between them. This is the maximum difference between them. If I take anything that is in between, they will be in between here. So this is N2, this is N infinity. Anything that I take in between will be between N2 and N infinity. Okay. So if I conduct an experiment and I find out, it is possible for me to appropriately choose N, M, where M I can choose appropriately. What I know for a two-dimensional space, which is something that I have done over and over, is the Morse circle. Yes? Yeah?
Yes, sir.
yes, sir.
So Morse circle represents, for example, if this is the Morse circle that I have, Morse circle represents the values of sigma and tau on planes that connects something like this at an angle which is
Theta.
twice that angle to the plane. This is something that we know. In this, supposing I have to represent Tresca condition. Tresca condition says that find out the maximum shear, and that has to go to a limit. Or in other words, whether it is like this or any other, I am only saying that tau equals constant. What tau? Tau max is my Tresca condition. Are you able to see this?
Yes, sir.
Yes, sir.
Tau max is equal to a constant. This is due to Tresca. Okay. So irrespective of whether the Mohr circle is here or Mohr circle is here or here, it does not matter. The moment the stress circle reaches this value, this reaches this value, yielding starts to occur. Understood?
Yes, sir.
Now, I'm going to make another statement here. This means it is independent of sigma. Is it not?
Yes, sir.
Because it has no role to play what is sigma 1, what is sigma 2. But it plays a role only in the difference between sigma 1 and sigma 2. Yeah?
Yes.
Yes, sir.
So, in the...
You mean failure?
Yeah?
You mean to say failure is independent of sigma?
So this is the yield
Material
condition. This
failure.
is the yield line. If I draw in sigma tau space, this is nothing but the yield line.
Okay.
Okay. That is
Yes.
f of tau. See how I am writing. F of tau divided by kappa minus 1 is equal to 0. Same. The Tresca condition is what I have written in a little different fashion.
Okay.
Of course, this will depend on only the invariance.
Okay. Coordinate. Okay.
This is how I got this one, correct? Supposing I say, okay, all right, I'm not going to have kappa, but I'm going to have kappa as a function of pressure. As pressure varies, the kappa varies. Earlier, I had f of tau by kappa minus 1 is equal to 0. Now what I'll do is, I'm going to now generalize it and introduce pressure to this. Where is pressure in this Mohr circle?
Center of
It's the center.
Sir, any
But
point
take only two
exact-
dimensions.
Okay.
It is nothing but the center, is it not? Sigma 1
Yes, sir.
plus sigma 2 by 2. So what I'm now saying is, no. This is not how it will be. It will be a little different, where supposing kappa is an increasing function in terms of pressure. Let us say something like this. Let's say something like this. This is kappa of P, okay? Then, if my Mohr circle is here, it will be small like this. If my Mohr circle is here, it will be big here. What am I saying? I'm saying, if I say kappa of P, what I'm saying is f of tau is equal to kappa of this. So this is nothing but f sorry.
Of
Tau is equal to KFP. Here it was a constant. Here it's a function of pressure. This is due to more Coulomb criterion, where there is a dependence on the pressure, on the triaxial state of the material. You get the idea?
sure.
In general, for example, if it is soil or concrete or whatever, compression takes a big role. So they would write minus sigma here and tau here to represent compressive pressure. Beyond this, it cannot take any load. It starts from here, it goes like this. If there is zero pressure, then there will be a value here that I can do the testing without any triaxial pressure. If it is soil, what they do is they do the test at a different value of the triaxial pressure. In this, this is the line that defines yielding. This is due to Tosca and this is due to more Coulomb, because we are using more circle in order to draw more Coulomb picture. Coulomb is because friction introduces this dependence on pressure. One last thing before we part. What about von Mises? Sorry. In von Mises, we had root of J2 is equal to kappa, right? How do I now generalize this? Root of J2 is equal to kappa of pressure. Very good. Or in other words, I can write this as root of J2 divided by kappa of P minus 1 is equal to 0. Alright? Now, the simplest one would be root of J2 plus C times pressure is equal to a constant. Mind you, if you notice, there is one constant here, material constant 1. Material constant 1 and material constant 2. Are you able to see this?
How did we write that?
This is an example. We started with root of J2 is equal to a function of pressure, and if I take this pressure to be simply a linear function, I'll get it to be root of J2 plus some linear variation of P is equal to K. Yeah? If I do that, I will have two constants that I have to find out.
Yes, sir.
To find out two constants, how many tests should I do? I need to do at least two tests. So that I'll get two values. Correct?
Yes, sir.
Two tests of different conditions so that I can find out the two constants. If you go back to more Coulomb, it is the same here. If I take this as a linear function, then this kappa will be a linear function. I need to find out the slope of this. Correct? I need to find out the slope. I need to find out the ordinate of this. which means there are two different values that I need to find. This is called Drucker yield condition, yield function. Okay, due to Drucker. So generalization of von Mises would be Drucker. Generalization of Tresca would be
More Coulomb.
More Coulomb has been introduced to physically represent a frictional term coming into picture. Here to physically represent a pressure term coming into picture. There are more to it. We'll take a pass because we have